Hi friends, welcome to Make Studies, and let's talk about U factor or overall heat transfer coefficient. We will learn the concept of overall heat transfer coefficient and how to calculate step-by-step process and examples. Let's try to see the concept. Let us consider there is a room and you are sitting within a room and it's a very sunny weather. So what happens? Heat will fall on the room, especially on the external envelope like wall or window or door, whatever the external portion are there. So heat or the sun rays will fall on this and heat will transfer through that portion. It can transfer through the wall, it can transfer through the window or door. So whatever the envelope is present, heat will transfer through that envelope. So heat transfer through this wall from outside to inside. And this is the wall through which heat is transferred. Let us draw the wall here, and this is the heat, and after the wall the heat will be reduced. It means the wall will resist to enter the heat into the room. So all the heat content will not be able to enter within the room. Let's consider this resistance by the wall is R, and wall gives resistance to heat ingression, and U is the overall heat transfer coefficient. Then overall heat transfer coefficient is written as 1 by resistance or 1 by R. Here for this wall we are considering the resistance is R1, so overall heat transfer will be 1 by R1. Now if we put some layer on the wall, it means we increase the thickness of the wall with some other material, then the amount of heat entered in the room will be reduced. See, the outside heat content is reduced in the inside, so all the heat will not be entered within the room, so it will be reduced. And why it will be reduced? Because this extra layer will give resistance to heat input. So this is basically the wall, and after that this layer is added, and this is the outside heat and this is the inside heat transferred, so it is less. So the resistance of the original wall is R1 and the new layer resistance is R2. So what will be the total resistance of this composite wall? It will be R equal to R1 plus R2. So overall U factor will be 1 by resistance, so 1 by R is equal to 1 by R1 plus R2. Now if we add one more layer, then the heat ingression will be further reduced, because this layer also will give the resistance against the heat input. See, this is the wall and here this one is the additional layer. So this outside heat amount is not changed, it is the same, but the heat ingression within the room through this wall will be reduced. So this is the resistance of original wall R1 and R2, and this is the layer whose resistance is R3. So total resistance R equal to R1 plus R2 plus R3. So overall U value equal to 1 by R equal to 1 by R1 plus R2 plus R3. So from this example we see the resistance is increased when we increase the layer or when we include some material over the wall, because this thick and multi-layer wall will give more resistance than the single layer of wall. This resistance helps to protect the heat ingression into the room. So from this example we can see overall heat transfer coefficient is nothing but the rate of heat flow through the building's envelope when a temperature difference exists. If the temperature difference doesn't exist, means both the temperature inside and outside are same, then there will not be any heat transfer. So this is basically overall heat transfer coefficient, and we have already seen it is written as U. And building envelope, it means the outside portion of the building, so the exterior part of the building. So this is the original layer of the wall, here is the first layer, and this is the second layer, and this is the outside heat, and here is the inside heat transfer into the room. Now these are three layers. So layer 1, it has resistance R1, layer 2, it has resistance R2, and layer 3, it has resistance R3. So total resistance, we have seen the summation of all the individual resistance like R1 plus R2 plus R3, and it is written as meter square K per watt. Now the heat transfer happens through the wall, and if the overall heat transfer coefficient is U, then we can write U is equal to 1 by R, and the unit of U value will be 1 by resistance units, that is watt per meter square K. It may be difficult to remember this watt per meter square K or meter square K per watt. Let's try to understand how to remember the units of overall heat transfer coefficient. So for example, this is a wall and its outside temperature is T1 and inside temperature is T2, and the difference between this outside and inside temperature is delta T, that is T1 minus T2, and heat is transferred naturally from outside to inside. And let's consider the Q amount of heat is transferred through the wall. If the area of the wall is A, then we can write Q equal to U A delta T, where Q equal to heat transfer, U equal to overall heat transfer coefficient, A surface area, and delta T temperature difference. So Q equal to UAT. Now unit of heat transfer is watt or W, and we have to find out the unit for U value or overall heat transfer coefficient. Unit of area is meter square, and temperature difference is degree centigrade or K, that is Kelvin. Remember, this temperature difference can be degree centigrade or can be Kelvin. There will not be any change of the value. So we get Q equal to UA delta T. If we put all the units here, W equal to U, and area unit is meter square, delta T unit is K. So we can write U equal to W or watt per meter squared K. So we understand that overall heat transfer coefficient means the rate of heat flow through the building envelope. If you see this building, we can see it has wall, it has roof, it has window, it has doors, it has shades. So there are so many of envelopes through which heat will be transferred. Now this is an example of a building. Let's see its envelope. So this is the building, and this portion, these are the wall. We can slightly make it big so that we can understand. So these are the wall, and this is the window. This is a window. Here is a window. Here is also a window. And this one, you see, this portion and this portion, these are shades. These are basically shades. This portion is shade. This portion is also shade. And this is the roof. It is at an angle. It is not horizontal roof. So these are the roofs. Here's a roof, here is a roof, and here is the roof. So this roof is at an angle.
Here if you see, this is the door, and the door has some glazing as well. So here also one window, and this is also window. Check this side. So these are the wall, and this is shared window, wall. You can check the back side. Yes, in the back side we can see this is the slopey roof, and this is the window, and this is the door. Let's see clearly. So this is basically door. So these are basically the envelope of a building through which heat is transferred.
So we have seen that heat transfer can be happen through wall, through partition, through door, through window, through shade, through air films, through insulation, through metals. Now this is a wall, and it's a typical example of a 3D model of a wall. And if you see the 3D view or its section, it looks like this. It has multiple layers. Let's try to understand the layers of the wall. So this is basically concrete. This is air gap. Air gap is very essential to reduce the heat transfer into the building as it has a resistance. Then insulation, and then brick, and there will be outside plaster, and here is the inside plaster. Now if we see the simple ray diagram, we can understand the configuration of a wall. So this is the concrete block, this is the air gap, this is insulation, this is brick, these are the plasters, here is the inside plaster, and here is the outside plaster, and air will be outside the plaster and inside the plaster as well. Here is the inside air layer, and this is the outside air roof. So this is a typical cross section of a roof, for example. So this is the concrete slab, this is screed, this one is vapor barrier, here is the insulation, this is polyethylene film, and then it is concrete layer. For the same thing, if we see a cross section of a floor, we see that there is a concrete layer, then it's a polyethylene film, and some screed. Now the material or type of the layer or the thickness of the layer, it depends on the project requirements. It can be varied by project to project and client to client. Many client wants energy efficient wall or floor or roof. They put a good insulation and multiple layers so that heat ingression will be reduced. Calculation example of a typical wall. So this is the typical wall cross section. This is inside of the wall and this is outside of the wall. This is the diagram. So at the inside there will be a layer of air. So inside air, let's try to find out the resistance. The unit is SI, meter square K per watt. If we see the ASHRAE fundamentals 2021 surface film coefficients, we see the table number 10, that is surface film coefficient or resistance. So this is basically the table from which we have to get the data. So the position of surface, look at this wall, it is vertical. So the position of surface, we see that it is vertical. Now direction of heat flow. So the outside temperature is hot and inside temperature is comparatively less. So there will be a heat transfer from outside to inside. So the heat will flow horizontally. So we select direction of heat flow horizontal. Now we consider non-reflective surface. So the resistance of the inside air will be 0.12. So the value of R1 equal to 0.12 meter square key per watt. Now the next layer, that is plaster board. It is called inside plaster because it is towards inside and its thickness is 15 millimeter. Let's go to gypsum plaster. So here is the building and insulating materials as per ASRE 2021 fundamentals. So building materials and insulation. So here is the gypsum or plaster board. Now the conductivity, gypsum board or plaster board. So density 640 and conductivity is watt per meter K, that is 0.16. So resistance is not given, so we have to find out the resistance from the conductivity. Let's try to understand how to calculate resistance from the conductivity. So it is gypsum board. Now conductivity value is 0.16 and the thickness we have got T equal to 15 millimeter. That means 15 by 1000 equal to 0.015 meter. So resistance will be T by K equal to 0.015 by 0.16. It gives 0.09375. So this is the U value of inside plaster. So R2 for inside plaster equal to 0.09375 meter square K per W. Now the third layer, that is concrete block with 200 millimeter thickness. It's a solid concrete block with 200 millimeter thickness. Let's go to the ASRE 2021 fundamentals, masonry materials. Here is the concrete block. Now let's try to find out. So we have to find out which one is applicable for our project. So here for our project it is 200 mm thick concrete block and it is the one which we are looking for. So it is 0.35. So the resistance for the concrete block with 200 mm thickness R3 equal to 0.35 meter square K per watt. Now the next layer is air gap. It is basically the standard value. So we can consider R4 equal to 0.16 meter square K per watt. And now the next layer is insulation. It is one of the main layer which gives maximum resistance. So insulation here, extruded polystyrene insulation with 50 mm thickness is used. Let's go to ASRE fundamentals, find out the insulating materials. Let's find out. So insulating materials, let's see. Okay, here it is extruded polystyrene. This is the conductivity of insulation, that is 0.029. Let's try to find out the resistance from the conductivity. Let's go to the Excel. So here extruded polystyrene insulation. So the conductivity K equal to 0.029 and the thickness here it is 50 mm. So 50 divided by 1000 in meters. So 0.05 meters. And the resistance, as per the formula we can write, it is T by K. So T means 0.05 and K means 0.029. So it comes 1.724. So the resistance for insulation R5 equal to 1.724. Now the next layer is brick. Here 100 mm thick brick is used. Let's see the resistance from ASRE fundamentals. Let's go to masonry materials. So here this is brick and based on our consideration, or if it is 2080, then it ranges from 0.92 to 1.12. For our case, based on the density, 1.12 is the suitable value. So let's try to calculate the resistance for this conductivity. Here's the brick. So conductivity is 1.12 as per ASRE chart, and thickness it is 100 millimeter. So 100 by 1000 equal to 0.1 meter. Now the resistance equal to T by K. That means the thickness 0.1 divided by conductivity 1.12. So it gives 0.0892857. So we can write 0.0893. So the resistance for the brick R6 equal to 0.0893. Now the next layer, that is the outside plaster, it is the same like inside plaster of same thickness 15 mm. So the resistance will be same. So the outside plaster 15 mm thickness, resistance R7 equal to 0.09375. Now the next layer, that is air. It is basically outside air. Let us try to find out the resistance of the outside air from ASRE Fundamentals 2021. From the ASRE, you see, for outdoor there are two options for winter and summer, and we select for summer, that is 0.044. So here the resistance for outdoor air is R8, that is 0.044. So the total resistance we can calculate. Total resistance R equal to R1 plus R2 plus R3 plus R4 plus R5 plus R6 plus R7 plus R8. Now if we put the value of R1 to R8, we can get 0.12 plus 0.09375 plus 0.35 plus 0.16 plus 1.724 plus 0.0893 plus 0.9375 plus 0.44. So if we add this value, we will get the total resistance equal to 2.6748 meter square K per watt. So the resistance 2.6748 meter square K per watt, and we know the overall heat transfer coefficient U equal to 1 by R. If we put the value of R here, we will get U equal to 1 by 2.6748, or U is equal to 0.374 watt per meter square K. So this is the final U value of a valve. I hope you enjoyed this video. So thank you so much.